Okay, hi folks. My name is John O'Reilly. I live in Galway in the west of Ireland and work remotely for Kotlin Technology based here in London. So we're going to talk today about various patterns and capabilities that we can apply when using Kotlin and Compose Multiplatform on iOS. We start by giving a basic introduction to the ecosystem and talk about the default Swift Kotlin interop we get out of the box. This has a number of limitations, and we'll then cover the capabilities that the Sky framework provides to address those, and talk about also some of the other sort of interop options that we available to us there. We'll also talk about the emerging Swift export functionality that JetBrains is developing to improve that interop. Next up, concurrency. Again, we'll talk about the limited interop support we get by default, and then the third-party solutions we can use for this, including use of Swift and shared KMP code is something we often need to do. And we'll cover some examples of how to achieve that. Similarly then for Compose Multiplatform, showing, for example, how we can include use of Compose in Swift UI and vice versa. We'll talk a little bit about background work on iOS, some of the KMP, CMP testing options available to us, and a few items related to developer experience. We'll finish up then with some info on build, packaging, and publication of KMP-based iOS apps. So starting off with a few basic definitions. This is how KMP is described in the official docs. It's basically providing a mechanism for writing shared Kotlin code that can be built and run natively on a wide variety of platforms. So first show of hands, how many people here have used KMP? Okay, quite a lot. Probably not too unexpected these days. Next up, Compose Multiplatform. This is a declarative UI framework for sharing UI across multiple platforms, based on Kotlin Multiplatform and Jetpack Compose. Another quick show of hands, how many people here have used CMP? Okay, great. Nice, quite a lot as well. Just to mention at this point that many of the examples shown in the talk today are taken from various KMP and CMP samples I've been working on, along with other folks, over the last 6 years. These all include iOS clients and also have varying degrees of use of shared Compose Multiplatform UI. Collectively, they're designed to cover a range of different code sharing scenarios. I'll also touch on some examples we're using in a Compose Multiplatform application we've been developing at Kraken. So with KMP and CMP, we have an almost continuous spectrum of code sharing possibilities. I wanted to show here a few points along that spectrum. On the left, we have a small amount of shared KMP code, along with a Swift UI client and Swift view models, for example. In the middle case, most of the logic is shared, including the view models, with potentially some shared CMP UI code, maybe a particular screen or just some part of a screen. And finally, on the right, we're sharing most of the code, including the UI, using CMP, with potentially some Swift UI as needed. It's important to note that our interop requirements vary considerably depending on what point along the spectrum we're targeting. And this, by the way, is roughly where the various samples I listed earlier fit in the spectrum. They're designed, as mentioned, to cover a range of different code sharing and interop scenarios, and we'll touch on a number of these in the talk today. Okay, we're going to focus now on the development of iOS apps using KMP. And a key component of the Kotlin toolchain that supports that is Kotlin Native. It's described as a technology for compiling Kotlin code to native binaries, which can run without a virtual machine. It includes an LLVM-based backend for the Kotlin compiler and a native implementation of the Kotlin standard library. It also importantly provides bidirectional interoperability with Swift and Objective-C. You can both use Objective-C frameworks and libraries in Kotlin code and Kotlin modules in Swift and Objective-C code. And what this typically means in an iOS project is that an iOS framework is generated from our shared Kotlin code. And that framework can be consumed in an Xcode project, for example. Also, an important aspect of the solution is that interop between Swift and Kotlin is currently based on an Objective-C bridge. This is an evolving area, and with the development of Swift export, we'll soon have direct Swift Kotlin interop. So in most KMP projects, we'll need to access platform-specific capabilities. And a key component for allowing that is the expect actual mechanism. We can expect a particular API, for example, to be available in common platform-agnostic code, and provide then the necessary platform-specific implementations for that. And how we manage that then is through various source sets in our KMP modules. We common main for our platform-agnostic code, and then platform-specific source sets for each platform. So first, small expect actual example. Here we have a get country name expect function that we can invoke in common main code. And then we have actual implementations for Android and iOS in their respective source sets, using locale on Android, and NS-locale on iOS. Another expect actual example, this time showing how we can create platform-specific dependencies when using the coin DI framework. We have a common coin module, and then a module specific to each platform, again, using expect actual. In the iOS case here, for example, we define platform-specific dependencies for KTOR, data store, and room. And this is how that create data store, for example, is implemented for iOS. The specific details aren't too important, but just to note again that we have access to the likes of NS File Manager to allow us to interface with the iOS file system from Kotlin code in iOS main. Also important to note that we can use the same approach for compose code, as we'll see in more detail later. Here we have this ISS map view expect function, which we can use in common main compose code, with actual implementations then for each platform. And we'll dig deeper into this example later in the talk. So the default and ideal is to have any shared iOS specific code in the iOS main source set in our KMP modules. We'll be talking, of course, about some cases where this isn't sufficient, but important to note that Kotlin Native comes with a large set of pre-imported iOS system frameworks that we can call from Kotlin code in iOS main if needed. So just starting off giving a few examples here of some of the default Kotlin Swift type mapping we get when using Kotlin Native, again through that Objective-C bridge. Class in Kotlin maps to class in Swift, with interface mapping to protocol, and interop using these is quite seamless. Where we start to see some disconnect is with sealed classes, for example, with some functionality lost in the default mapping to a Swift class, for example, exhaustivity checking. And we'll talk shortly about how that and other disconnects can be addressed using third-party solutions. Just showing then the mappings of some of the basic types. Again, these map quite seamlessly. And lastly, some examples of collection types being mapped. Kotlin list to Swift array, set to set, and map to dictionary. And a small example then of calling a KMP code from Swift that returns a Kotlin list, which can then be assigned directly to a Swift array. We mentioned some of the disconnects that exist when using the default approach for mapping between Kotlin and Swift. And one popular third-party solution that's emerged to address that is Sky, standing for Swift Kotlin Interop Enhancer. It's one of a suite of solutions that TouchLab have developed for KMP that have become indispensable. Included in what Sky supports are enums, sealed classes, as we mentioned earlier, default arguments, global functions, overloaded functions, and coroutines interop, which we'll talk about in more detail in the concurrency section later. So starting off with the example of sealed classes. These are, of course, an important part of the Kotlin language, frequently used, for example, for encapsulating UI state as shown here. And a key aspect of what they provide is exhaustivity checking, which we don't, as mentioned, get in the default mapping that Kotlin Native provides. With Sky, this Swift onEnum function is automatically generated for us, which allows that check to occur. And we see, for example, in Swift code and Xcode, if we try to remove one of the cases, resulting in this switch must be exhaustive error. Another small example is global functions. Without Sky, we have to prefix the function in Swift with the Kotlin file name. Sky removes the need for that. I mentioned earlier that existing Swift Kotlin interop is currently done through an Objective-C bridge. With Swift export, JetBrains is working to provide direct bindings. It's very exciting to see this develop. So these are the Swift export features that were included in the recent Kotlin 2.2.20 release. This is still work in progress and somewhat experimental, but a very significant first step. And this is what will be included in Kotlin 2.3 and later. It was originally hoped that suspend function support would be in 2.3.0, but looks like it'll be in later now. It's also very important to note that in the absence of concurrency functionality in current Kotlin versions, you'll still likely need to use one of the third-party solutions we'll be talking about shortly, and these typically don't work alongside Swift export. By the way, I've started trying out Swift export in the Chip 8 sample I have, and just a few excerpts of some of the changes needed. We have a new Swift export section in the Gradle build, and new embed Swift export for Xcode Gradle task invoked from an Xcode run script. Okay, next up, concurrency. So just to start off by giving some background on the structured concurrency functionality that we now have in both Kotlin and Swift before we talk about interop between them. This is a really powerful capability that allows us to write async code in a way that's easy to read, and also allows a more deterministic, structured approach to error handling and cancellation, for example. A key enabler of this is the ability to have code that can be suspended at particular points and resumed later. Swift supports these capabilities through the likes of tasks, async functions, and async sequence, and Kotlin similarly through coroutines, suspend functions, and flows. And a very important aspect of this approach is how invocation of code like this can be tied into our UI lifecycle, thus allowing, for example, automatic cancellation when a view disappears. So just a few small examples of how we would invoke async code in Swift and Kotlin. We can invoke from a function that's marked as async in Swift or suspend in Kotlin. We can also create a specific task in Swift, and similarly in Kotlin, create a coroutine from which the code can be invoked. We can also, as mentioned, tie invocation of async code to our UI lifecycle on both platforms, along importantly then with automatic cancellation when the UI is no longer shown. We can use a task view modifier in Swift UI for this, and can use, for example, launched effect in Compose. Also showing examples of async sequence in Swift and flow in Kotlin. We use for await in Swift to iterate over the stream of values, and use collect in Kotlin to do the same thing. And then also a few examples of some of the operators. Firstly, using map in both Kotlin and Swift to convert each value to its uppercase version, and again iterating over the result. And then filter, for example, to filter on a particular string, again in a very similar manner. Okay, now I'm going to talk about some of the concurrency interop options we have available to us. We'll briefly cover the limited default behavior we get out of the box with Kotlin Native, and then talk about a few third-party solutions that have become established to support this interop. So by default, Kotlin suspend functions are represented as Objective-C methods with completion handlers, or callbacks, which, by the way, can also be called from Swift as async functions since Swift 5.5. These do have some limitations, though, such as, for example, the fact that cancellations are not propagated. Not going to focus too much on this approach, as there's third-party solutions that are generally used these days to provide concurrency interop, as we'll see shortly. Just to mention that the current official guidance from JetBrains is also to use these third-party solutions, such as KMP, native coroutines, and Sky. And as mentioned here, both of these libraries support proper cancellation of coroutines. By the way, we're focusing here on interop with the Swift structured concurrency capabilities added in Swift 5.5, as they map quite nicely to how structured concurrency works in Kotlin. There are also, through these libraries, ways to support other iOS concurrency frameworks such as Combine and Oryx Swift. Okay, so first of these alternatives is KMP native coroutines. It was one of the first solutions created that provided interop for both suspend functions and flows, along with providing that cancellation support. For suspend functions, we annotate our Kotlin functions with @native coroutines, and then in Swift use the library's async function to invoke, and can use then with Swift's await. Likewise with flows. In this case, using the library's async sequence function to convert the Kotlin flow to a Swift async sequence. And can you then use Swift's for await in this case to iterate over the values collected from that Kotlin flow. Next up is KMP observable view model. This, by the way, was previously known as KMM view model. It's now described as a library to use Android X Kotlin view models with SwiftUI, given availability now of KMP version of the Jetpack view model library. And the key aspect of what this offers is the ability to expose Kotlin state flows, for example, as Swift properties that can be directly observed in SwiftUI, as we'll see next. So this is an example of one of the shared Jetpack view models in the bike share KMP sample. In this case, exposing the list of countries we're displaying. We're using our repository class to get the list of countries, doing some transformation of that information, and exposing then as a state flow. And this is how that's consumed in SwiftUI in the iOS client. We instantiate the view model we saw in the previous slide using the state view model property wrapper provided by the library, which then allows that country list state flow from the Kotlin view model to be observed directly here as a Swift property. And any changes to that will cause our UI to be recomposed. As with KMP native coroutines, Sky also supports concurrency interop with Kotlin, showing here again how we'd invoke a Kotlin suspend function from Swift. With the approach that Sky takes using KSP, it can provide a more seamless interaction with Swift, as we can see here, with no additional wrapper functions needed. And likewise for consuming Kotlin flows from Swift. We have a Kotlin state flow shown here, and can use Swift's for await to collect values from it. Another related piece of functionality that Sky provides is the ability to observe Kotlin flows in SwiftUI as if they were Swift properties, quite similar to functionality that the KMP observable view model library provides. Here, we're observing in SwiftUI the UI state flow from our Kotlin view model, and again, the UI will be recomposed if that changes. Next up, we're going to outline some patterns for using Swift in shared Kotlin code. So a key enabler for this is the ability to have a Swift class. The key enabler for this is the ability for a Swift class to subclass a Kotlin interface, and that implementation then to be passed to and used from shared KMP code. And this approach is the basis for most of the interop scenarios we'll be describing in this section. Starting off with a small example from the Firebase AI logic sample I have. So this is a Compose Multiplatform project with most of the code shared between Android and iOS. The screenshot here is from the iOS app. Here we have a Kotlin interface, generative model, defined a common main in our KMP module, in this case being used to generate images using the AI logic SDK. And this is the implementation on Android, using the associated Firebase Android Gradle dependencies. By the way, you might have seen an example of this using this API. You might have seen an example of using this API as well at Yolanda's very nice talk yesterday. It creates an image model using that library, and from that generates an image using the supplied prompt. And we can implement that same Kotlin interface in Swift code, this time making use of APIs from the Firebase Swift package to do the same thing. Note again here that generative model is a Kotlin interface. Note we're using Sky here, which makes the concurrency aspects of this quite seamless. We override the Kotlin suspend function. We override the suspend function in the Kotlin interface with an async one in Swift, and can use Swift's await when invoking the Firebase API. We're also making use of a helper function in shared Kotlin code to convert the result to a Kotlin byte array. And this is an example then of how we can provide that generative model Swift implementation to our shared KMP code. In this case, we're providing it when we initialize the coin DI framework from Swift iOS code. That instance then becomes part of the coin object graph, and is what is injected into our command code when running on iOS. And here we see that generative model instance getting injected into the Kotlin view model in common main. Coin will inject the platform-specific instance of this depending on the platform we're running on. And finally, showing compose code using coil to display the generated image. And again, this is common code. Another common example is Firebase Analytics. Again, we define a Kotlin interface in shared common KMP code, along with an Android implementation in our Android main source set, again using the Firebase Android Gradle dependency in this case. And then implementation in Swift, making use of the Firebase Swift package. As before, Analytics here is a Kotlin interface. And again, we'll pass this Swift instance to shared Kotlin code, as we'll see next. In this case, we're using the Kotlin inject DI framework, passing in the Swift instance when creating the Kotlin inject component from iOS code. Using override here in that Kotlin inject component provides a very similar mechanism to ensure this instance becomes part of our object graph when running on iOS. And lastly in this section, a small example then from the confetti sample, using decompose component in this case. Here we're actually providing the Swift implementation as closures, which again we can use from shared Kotlin code. Another interesting approach that's emerged recently is the Swift Package Manager for Kotlin Multiplatform plugin. It provides the possibility, in certain cases, of actually consuming a Swift package from iOS main code. And hot off the press, JetBrains announced yesterday that they've prioritized support for consuming Swift packages in KMP, albeit with the limitations that the library I mentioned in the previous slide has, i.e. it has to be an Objective-C compatible library. Okay, next up we're going to talk about some of the UI interop options available to us when using Compose Multiplatform on iOS. We'll talk about how expect actual can be used again here for providing platform-specific implementations in shared code. We'll then give an overview of UIKit-based interop that's available, and how this forms the basis for allowing both consumption of Compose code in SwiftUI and SwiftUI code in Compose. By the way, for those who aren't aware, UIKit was the predecessor to SwiftUI. First, use of expect actual. So often this interop is done already for you using this approach in the increasing number of CMP libraries out there. For example, this is code that's using the Kscan barcode scanning library from Ismail Mohammed, a colleague of mine at Kraken. Under the hood, that library uses MLKit on Android and AV Foundation on iOS. The scanner view composable is defined as an expect function in common code. And then we have Android and iOS specific implementations in their respective source sets, using, as mentioned, MLKit for the implementation on Android and AV Foundation on iOS. But again, consumers of scanner view writing compose code in common main are abstracted from these platform differences. Next, we're going to talk a bit about UIKit-based interop. As mentioned, Compose Multiplatform is interoperable with the UIKit framework. We can embed Compose Multiplatform views within UIKit code, as well as embed native UIKit components within Compose Multiplatform. Combining this then with SwiftUI and Compose's own UIKit interop, we can in turn provide a way to consume Compose code in SwiftUI and vice versa. A key component we're going to be dealing with when performing that interop is UI view controller, a word you're going to hear me mentioning a lot in the next few slides. It's defined simply as an object that manages a view hierarchy for your UIKit app. So these are the key UIKit related classes that Compose Multiplatform and SwiftUI provide to allow us to implement that interop, based on using that UI view controller object as a bridge. For Compose Multiplatform, we have Compose UI View Controller. That's a CMP function that wraps Compose code in a UI View Controller. And UI Kit View Controller, which supports the reverse, allowing inclusion of a UI View Controller in a Compose view. And we have similar symmetry for SwiftUI with UI View Controller representable, which allows including a UI View Controller in SwiftUI, and UI Hosting Controller for wrapping SwiftUI as a UI View Controller. And another view of these same classes here showing the interop options they enable. Using SwiftUI's, these are all sort of long-winded names to say, but using SwiftUI's UI View Controller representable and CMP's Compose UI View Controller to allow consuming Compose code in SwiftUI. And similarly using CMP's UI Kit View Controller and SwiftUI's UI Hosting Controller to allow consuming SwiftUI code in Compose. Lots of moving parts that will hopefully become clear as we work through some examples. Okay, so let's firstly look at example of how we can consume Compose code in SwiftUI. This is our main SwiftUI view in this example. It includes Compose view, which is another SwiftUI view that will wrap around our Compose code, as we'll see next. By the way, it can be a little bit confusing, going back and forth between Swift and Kotlin. So using the color of the border of the code block here to indicate which, with red for Swift and purple for Kotlin. And shown at the top of the slide is the point we're at as we navigate up and down through the sets of components. Okay, and that Compose view we mentioned in the previous slide implements SwiftUI's UI View Controller representable, which allows including a UI View Controller in SwiftUI code. And it works here by invoking main view controller, a Kotlin function we have in our shared Compose code, from this make UI View Controller Swift function. And this is that main view controller Kotlin function. And that in turn is using CMP's Compose UI View Controller to wrap Compose code and return a UI View Controller to the invoking SwiftUI code. And this is the approach is the basis for most scenarios where we want to consume shared Compose code in SwiftUI. So just another quick show of hands. Has anyone had to do this in their projects yet? One lonely hand at the back, I think. Two even. And sorry to say, it gets messier. Where things get a lot more complicated, or well, a little more complicated, is when we want to consume SwiftUI views in our Compose code. And this is usually enabled through use of what you might have a native view factory class. This is a Swift class that implements a Kotlin interface and is responsible for creating SwiftUI views that our CMP code can use. The general approach here is the same as we mentioned earlier for consuming Swift in shared KMP code, with an instance of that view factory being passed to and used from shared KMP code in this case. So going to illustrate this using an example from the People in Space CMP sample, where we're showing the position of the International Space Station in a SwiftUI map. Here we have an outer SwiftUI shell that just basically includes a title bar. That in turn uses Compose Multiplatform for the content area, which in turn uses SwiftUI for the map. So this is a somewhat contrived example, but is designed to hopefully illustrate the various moving parts needed to support this type of interop. So the first part, consuming the shared compose code in SwiftUI is much the same as we saw in the earlier example. We have our outer SwiftUI view that in this case includes just a navigation view with a title bar. And also compose view, which, as before, is a SwiftUI view which will wrap around our compose multi-platform code. And again, that Swift compose view implements UI view controller representable and invokes the ISS position content view controller Kotlin function that's in our shared CMP code. In this case, we're also passing down our view model and the native view factory instance we mentioned earlier. That Kotlin ISS position content view controller function, that in turn, as we saw before, uses CMP's compose UI view controller to wrap the shared compose code, ISS position content in this case, as a UI view controller, which can be included in SwiftUI. Note we're using composition local provider here to ensure the native view factory instance we're passing down is available in compose code that needs it. More about that later. And this is that ISS position content composable. It has some basic UI for showing the position of the International Space Station in compose text view. And also, importantly, includes ISS map view composable, which will ultimately wrap our SwiftUI map. Okay, now going the other direction. And just showing again here the key components that allow us to consume SwiftUI in CMP code, using CMP's UI kit, view controller, and SwiftUI's UI hosting controller. Okay, so showing here that ISS position content composable again. And as mentioned, it includes the ISS map view composable, which wraps our SwiftUI map. And that ISS map view, in turn, uses CMP's UI kit view controller to allow including a UI view controller in compose code. It does that by using the Swift native view factory we passed down to create that UI view controller, which in turn wraps the SwiftUI map. Specifically, it calls the create ISS map view Swift function, which we'll see shortly. Note also that the view model we passed down from SwiftUI is being passed back up. It contains the position information which we'll need to observe and show on the SwiftUI map. Okay, we're nearly there. We're back up in Swift code again, and this is the native view factory and that create ISS map view function we just invoked from compose code. That's going to use SwiftUI's UI hosting controller to wrap the SwiftUI map implementation and return a UI view controller that can be included in our compose code. And finally, we have that SwiftUI map view. Note that we're also using Sky's observing here to observe the position information from our Kotlin view model, which we'll show then in the map as it changes. Another approach you can take for this type of interop, in particular when using SwiftUI views in compose code, is compose Swift bridge from TouchLab, which abstracts you from some of the details we just showed. Okay, finishing this section with a small example of how common compose multi-platform adaptive layouts work equally well on iOS. This is the My Mac designed for iPad version of the Confetti CMP app. And you see here an example of how we can easily use CMP's adaptive libraries to dynamically switch between different layouts depending on the screen size, switching between a list and a grid view in this case. Okay, next up I'm going to talk a little bit about how we can run background tasks on iOS in a KMP and CMP app. So there are two basic types of background tasks on iOS, BG app refresh task and BG processing task. BG app refresh task is typically for short duration tasks that expect quick results, and whereas BG processing task is for tasks that might be time consuming, such as downloading a large file or synchronizing data. Another quick show of hands, how many people here have used background tasks on iOS? Okay, three hands, cool. Showing here then how we firstly need to enable the background capabilities in Xcode, and also how identifiers for any background tasks we create need to be added to the info.p list. Okay, so starting off by showing an example of how we can run, say, a nightly refresh, triggered from SwiftUI using relatively new background task view modifier, but invoking then shared KMP code to do the work. When the app goes into the background, we schedule the refresh. That's done using this schedule data refresh method here, using BG task scheduler to schedule the request. Note that refresh data string shown here is the identifier that we added to the info.p list. Very important to remember to add that. And then showing shell of the shared Kotlin code that the background task is invoking. Another approach is to create and schedule the tasks in iOS main in shared KMP code. There's also a nice example of doing that in Chris Bain's TV sample, and we're also doing something similar for our CMP project at Kraken. Another useful API we can use in iOS main is begin background task with name. This allows us to mark the start of a task that should continue if the app enters the background. We also get notified if remaining time is running out and can, for example, schedule a background task if that happens. Next up, I'm going to take a quick look at some of the testing options available to us for CMP and KMP apps. These options include running KMP unit tests, CMP UI unit tests, Swift tests that invoke shared KMP code, and also want to show an example of a nice UI testing framework called Maestro that we can use to test both our iOS and Android CMP apps, for example. So first option we have here is running unit tests in common KMP code from our common test source set. These can then be run for various platforms we're targeting. Note that we can also add, for example, iOS test source set. Here, if we want to run iOS tests that need to test code that's in iOS main. A very nice capability we also have now is the ability to run CMP UI unit tests, again from common test, and also with option to run on different platforms. Another option then, depending on our requirements, is to run Swift tests that in turn invoke shared KMP code, as we're doing here in the Confetti project. And lastly, Maestro, a really nice UI testing framework that wraps around UI Automator on Android and XCTest on iOS. We can run the same script for both iOS and Android CMP clients, for example, with option as well to run certain steps for each platform as needed. By the way, anyone using Maestro here? Okay, quite a few, nice. Okay, next up, a few items related to developer experience. Yet another TouchLab tool that I'd definitely recommend using is Xcode Kotlin. This is a plugin that allows browsing and debugging Kotlin code from within Xcode. Here we see, for example, case where we've added Kotlin source set to Xcode and have been able to set breakpoints in Kotlin code and view variables, etc. Really useful tool to have. Another really nice option we have these days is the KMP plugin from JetBrains. This allows running an iOS app from Android Studio or IntelliJ, setting breakpoints in Swift code, stepping between Swift and Kotlin, and looking at variables, etc. Example here from the Confetti project. Lastly, in this section, showing a small example of how we can view documentation that's in our Kotlin code from within Xcode. We just need to ensure we set this option in our Gradle file, after which we're able to see the documentation in Xcode as shown here. Okay, in this last section, we're going to cover some topics around the building, packaging, and publication of iOS apps that use KMP and CMP. So there's typically two main approaches used for building and consumption of KMP shared code. The first one here is usually based on a single repository containing both the shared and the client code. In this case, we build the iOS project, the iOS framework directly, and consume it within the Xcode project. And the building of the shared code as an iOS framework is triggered through an Xcode run script like this, using KMP's embed and sign app framework for Xcode Gradle task. The other approach is typically used when there's separate teams for the client and the shared code, and usually involves separate repositories for each. Here, a Swift package is created from the shared code, excuse me, and published to a remote repository, along potentially with some cloud storage for the XC framework zip file that's part of the package. That package then can be added to an Xcode project using, for example, the GitHub repository that the package is published to, as shown here, for example, with the BikeShare Swift package repo. The Swift package in this example for the BikeShare project was built using the Multiplatform Swift package plugin. The plugin automatically creates the associated XC framework and package Swift files. The publication of these artifacts, though, needs to be managed separately. Another solution many teams are using now for this is KMembridge, or Cambridge as it's known, from also TouchLab. This also creates the XC framework from the shared code, but also supports a range of options for managing the publication. Next up, umbrella modules. Typically, we need to expose a single iOS framework, but what do we do if the shared code is split across multiple modules, as is frequently the case? The solution generally recommended here is to create what's called an umbrella module for which a single framework is built but includes code from other modules as shown here. Note, by the way, that Swift export will support generating and exposing multiple modules. Now I'm going to talk a little bit about building, publishing iOS apps in CI. Folks might be familiar from using Fastlane on Android, but it also has a ton of really nice iOS-related integrations as well. And we'll show a few examples here. Another quick show of hands, how many people are using Fastlane? Okay, quite a lot is expected. So what we typically want to do is build, sign, and publish the iOS app to App Store Connect. Initially to test flight for internal and beta testing, and then to production. So Fastlane provides a nice action to build the IPA file that's needed for publication as shown here. And then a task, for example, to publish that API to test flight. An important requirement when building, publishing iOS apps is, of course, how we sign them. And Fastlane provides a very nice option for doing this using a relatively new capability called Match. With this approach, we add our certificates and provisioning profiles to a dedicated private GitHub repository. And Match then provides a convenient way to both distribute those across the team and also use in CI. And a small example then of using Match in CI to automatically sync certificates so they can be used as part of the build. Okay, so today we talked about the various patterns and capabilities that we can apply when using Kotlin and Compose Multiplatform on iOS. We covered basic interop capabilities we get by default. These have some limitations, and we gave some examples of how these can be addressed using the Sky framework. And also talked about the promising Swift export work being done by JetBrains. Similarly with concurrency, again, we covered how a number of third-party solutions can be used to address the limited interop support we get by default. Next, we outlined some patterns for how we can include use of Swift in shared KMP code, and likewise then for Compose Multiplatform, showing various interop options available for including Compose in Swift UI and vice versa. We talked about background work on iOS, some of the KMP, CMP testing options available to us, and a few items related to developer experience. We finished up then with some info on the build, packaging, and publication, again focusing on iOS aspects of this. Thank you.